that is not really a lake, is just maybe dust, filled it up even more, and then the climate of Mars changed in a way where no longer were things being brought into the crater, but now wind was scouring stuff out of the crater. And it scoured it out in a way that sort of dug this big pit into what was a full crater at one point, leaving this dusty stuff here, and then the layers of lake sediments that we're now studying climbing up this way. So these lake sediments would have gone all the way across when the lake was filling it, but all this has been removed over eons by wind. So that's our story. We're sticking to it. And we're continually finding evidence to support it and making our case to the rest of the scientific community through the usual process, lots of peer-reviewed papers. But so far, when we run these ideas by Earth geologists, who of course can do a lot more advanced stuff than we can do on Mars, they think we have a pretty good idea of what we're seeing. So we've now driven about 18 kilometers, so 11, 12 miles on the ground. We landed out here on the plains. This is a map looking down. These are the plains we landed in. This is the mountain and all the layers of the mountain. So we landed out here. We made all those discoveries right where we landed at Yellowknife Bay. Then we drove pretty fast, found those deltas kind of in here. We got to the edge of the mountain about 2 years into the mission, and for the last 3 years, we've been slowly going up all the layers of the mountain, little by little. We're here right now, and we'd like to do this remaining segment before the mission ends. So hopefully we'll be able to do all this in the next 2 or 3 years, and once we get up to this layer, we will have studied all the layers on the mountain that appear to have formed through water. So far we've drilled about 15 holes. Here's 12 of them, and you can see there's kind of a variety. There's holes that the material is reddish when we drill it, so maybe the oxidation has penetrated into the rock. There's holes that most of them are pretty gray, and in those gray holes is where we tend to find the clay minerals and even organic molecules, very simple carbon-containing molecules that have survived because they haven't been oxidized and destroyed. And then we found a couple more red holes lately. I think the next few slides are a little bit more of a tour, just my favorite pictures. But just to give you a sense of the variety of things that we're seeing as we've been driving along the last few years. Here is a nice picture showing 3 materials that we've gotten very used to seeing that are very different from each other. The first thing you see here is this pale bedrock that's very smooth. Those are the lake deposits. And when we look up close at these, they have those millimeter scale layers that tell us they were lake deposits. Above them in this area, there's this very rugged sandstone. This is a rock that was once loose sand that's now cemented together. This particular sandstone is very much consistent with being driven by wind, as opposed to those deltas that were water. This is an ancient dune field, sand dunes, that were there 2-3 billion years ago that have now turned into solid rock. And then the third thing you see here is modern sand. So this is just sand that's blowing around today. And so, when we're driving around, we have to sort of mentally ignore the modern stuff. It's not that interesting. We have to find the places where the lake deposits are exposed at the surface and we go study them. And then we have to understand how this later stuff covered up some of the lake deposits and how it's related in time. This is one of my favorite pictures. These are the Murray Buttes. These are several stories high. These big buttes that we drove through. It's like you're driving through Utah or somewhere. Bugs Bunny and Roadrunner country. And you're driving through here. These are those lake deposits. And again, the sandstone is above them. And the reason you get these buttes, whether you're talking about New Mexico, Utah, or Mars, is because the sandstone is a little bit more resistant to erosion. So even though most of it's gone, these layers used to connect at one point. The sandstone is a little bit of armor that's protecting the rest of the stuff from being eroded away. So you get these little towers. But eventually, another billion years, these will be gone too, leaving these lake deposits exposed. Here's the thing we saw at the beginning, the selfie. What's neat about this is we studied some of these modern sand dunes. It was actually the first time we've ever seen modern sand blowing around on Mars. The other rovers have seen ancient dune fields, but we actually were able to drive up to dune fields and watch them actually moving, which was really cool too. Even though it has really nothing to do with life and our main goals of the mission, we're on Mars, you got to study it. And so we did some playing around, we dug some trenches, we watched sand avalanche, we watched sand blow, and one of the things we discovered was that, not surprisingly, there's a lot of similarities to sand dunes on Earth. The dunes have similar shapes because the physics is roughly the same, even if you have a thinner atmosphere and a little less gravity. But one thing that you do not find on Earth are these ripples. You find these small ripples. You see those here. You go to Death Valley, you'll see dunes covered by these small ripples that are maybe a few inches apart. What you won't find are this other set of ripples that are about 3 feet apart. And what it turns out that those only form in the thin atmosphere of Mars. The totally different physics comes into play with the thin atmosphere in this case. And so you really are on Mars when you see those, which is kind of neat. This is just showing you some results from our weather station. What's plotted here, this is temperature in Celsius and Fahrenheit. Can't really read it, but I think it's minus 120 over here, and something 100 Fahrenheit over here. So this is Los Angeles over 2 years. And Los Angeles is nice and warm, and actually doesn't vary a whole lot from day to night. And this is Mars, to give you an idea of what the rover has to put up with every day. So Mars varies from summer to winter, like this, but the day-night differences are even bigger than the summer-winter differences. So every single day, now 2,000 days on Mars, and 5,000 days for Opportunity, the other rover, you have these very sensitive electronics, moving parts, all this kind of stuff that has to survive these 100-degree plus temperature changes from day to night. There's, you leave your laptop out overnight in LA and it wouldn't survive the next morning. So it's yet another way that the engineers just have to really do some amazing work to make these machines last in this really horrible, extreme environment of Mars. We found a meteor. We actually aren't the first rover to find these. It's not uncommon actually to drive across Mars and find meteors. And this is a big chunk of iron. We can shoot it with our laser, and we determined that it actually was an iron-nickel meteorite, which similar to iron meteorites you find on Earth. So that's kind of neat. Here's a picture of a rock slab. This is about 1 inch here, where we see all those thin layers that are similar to what you'd find in the lake bed, that we think are indicative of a lake, ancient lake bed. But within this particular slab, there are all these little pimples on it. And when we look close at those little bumps, they have these interesting shapes. And those shapes are very similar to what you'd find if you dug below an ancient lake on Earth, or even a current lake on Earth, where gypsum or other salts are crystallizing in the mud below the lake. And so we found these little swallowtail shapes that are very diagnostic of gypsum crystals, which is a kind of salt that forms in lake beds as they dry up. And these salts, these crystals were forming in the sediment. So yet another circumstantial piece of evidence that we are actually studying ancient lakes. On the opposite end of the spectrum, this is rare, but it's neat to see the whole picture. We found places where the lakes clearly disappeared. So this is a slab of rock that's made out of that same mudstone that formed through lakes. So it was once soaking wet mud that hardened into rock. But unlike the other ones that sort of hardened underground over time, this one hardened at the surface. Something happened where the lake shrunk, maybe, or it got warmer for a few days or a few years, and the top layer of mud on this particular slab cracked. just the same way you'd find mud cracks in a drying pond or something like that. So it was really neat to be able to like see these cracks, measure all of them, you compare all their angles to mud cracks on Earth, and figure out that these mud cracks probably formed in a single day on Mars. You know, so it's kind of cool to think, you know, that what we're seeing here, one day there was a lake, the lake receded for whatever reason, and in one day the mud cracked, and then it got buried, kind of like, you know, the mosquitoes in Jurassic Park. If the right conditions happen, you just bury it quickly and you preserve it, and 3 billion years later. we had naturally but more commonly formed because of life. So it's looking for biosignatures but not actively looking for living.
Okay. Yeah, a couple of quick questions. First, thanks for the great presentation. I'm planning on visiting JPL in the next couple of months, and I'm wondering, is it possible to see the twin Curiosity when I go down?
You can. We have two models of Curiosity, the real one and the fake one, kind of.
Okay.
So anybody can see a full-size wood and plastic model of Curiosity. That's one of the things that all the tour groups go see. So
Okay.
that's neat in itself because you can appreciate the size of it and look up close. It's pretty well made. The actual one that you saw in the video, and the one that's here, actually, this is in a place called the Mars Yard at JPL, which is like a football field-sized area that's made to be like Mars. It's the rover proving grounds. We have the test rovers climb hills and learn how to navigate, and that's where this model lives, which is the one that's very similar to the one actually on Mars. Because it's very precious, it spends most of its time in a shed and kind of not open to the public, but if you happen to be lucky, and maybe this is like half the time, it'll be out in the ground and you can see it.
Okay. Also, I was wondering, do you have an awareness, like right now, on the day-night cycle in Mars? Like, is Curiosity in daylight right now or nighttime? Do you know?
It would be probably in daylight now. Mars has a 24-and-a-half-hour day, believe it or not. It's coincidence. There's nothing magical about 24 hours. It just happens to have a 40-minute or so longer day than Earth, which means that we stay in sync with Mars for about 3 weeks, and then we are out of sync for about 3 weeks, and that's sort of the cycle. I'm going to digress because that's one of the things that we do when we land on Mars, the most efficient way to operate these missions, especially when you're worried about it dying and you have this precious thing that actually is on Mars, you want to stay in sync with it, so you get every minute out of it. So we actually live on Mars time for about 90 days, where we adjust our bodies to 24 and a half hours, or we try to anyway. You tape out your windows at home, you talk your family into it, and for about 90 days, you come to work 40 minutes later every day. And the reason it's 90 days is because everybody goes crazy after that. But at least for 90 days, you get to operate it maximally. And now we operate it every day for 3 weeks, and then when we're out of sync, we operate it every other day. And it turns out, it's a long answer to your question, we're out of sync when Mars and Earth are daylight at the same time. Because what we like to do is it's daylight on Mars, the rover's doing its thing while we're all sleeping.